Good morning, everyone. Can you hear me? Okay, so let's begin. Um, Good morning, Setu Selvi. Can you hear me?
Yes, sir. I'm
Okay,
here.
very good, very good. I can hear you as
Thank
well.
you, sir. Yeah.
So students will join as we go along. So we are live, and today's topic has got a long title. It is titled "Semi-supervised disentangling of causal factors." Okay, so it's a long title. And where we are is it's a subtopic within representation learning, which I feel is the most central topic from the point of view of future research for deep learning. And this subtopic relates a bit to what we covered last time, which was on transfer learning. But anyway, it stands on its own. So let me just see if I can define some other terms so we can put it all together and see what we're going to learn today. The first phrase is semi-supervised. Semi-supervised refers to a training data set that is not all labeled. Like we know the supervised learning problem, we have labeled examples of cats and dogs, and the network learns to recognize cats and dogs. Or we have labeled examples of handwritten digits, and the system learns to recognize handwritten digits. That is supervised learning. Semi-supervised learning means we have lots of data, but not all of it is labeled. So we don't know which one is a dog or a cat, or which one is a 0, 1, 2, 3, or 4. We just have lots of examples of 0, 1, 2, 3, 4, etc. We have lots of dogs and cats, and we don't know which one is which. Semi-supervised refers to how we could have a few of them labeled and not all of it. So that becomes a very useful situation in the world today when we have so much of data available, but not enough labor available to sit down and categorize them and label them and so on. So semi-supervised is about, well, we can do some. Can you pick up from where we left off and do the rest on your own? So that becomes semi-supervised. So that's the definition of the first part, semi-supervised. The second part says disentangling of causal factors. That itself is a very long phrase. It uses three words, disentangling, causal, and factors. So let's see, where shall we begin? With causal, we've seen a bit of it before. That causality has to do with cause and effect. So what is the cause and what is the effect? In terms of deep learning, we can think of it that the image we are seeing is the effect, and the cause is what is the object that is causing the effect. So if the cause is a handwritten digit 9, then the effect is some kind of an image of the digit 9, which might have some peculiarities to it, but it's been caused by the fact that it's supposed to be 9. Similarly, if we are looking at an image of a cat, and if the cause is the actual cat, so what we are actually seeing is an image of a cat, and the cause is the cat that caused that image. So this is about causality. So in a sense, you can see how it might relate to deep learning, where we're talking about an input is an image, X, and then we are going to into some kind of a representation at the next level. May not be the ultimate class, but something like the next level is the cause that caused this effect. If it is just directly the image, if the cat, then the cat is what caused it. So, but we can think of something intermediate as well. So that's the thing about causality. And the causal factors is there could be multiple factors that are causing it. It could be factors related to the amount, the thickness of the writing, for example, a handwritten digit, the kind of pencil or pen and so on. There's many causal reasons that create a particular object. So there could be more than one cause. And so we're talking about disentangling. What does disentanglement mean? That's again an intriguing term, which says when you have many causes mixed together, can you take them apart, disentangle? It's like some kind of ropes or something. They're all entangled. One is mixed up with the other, and what you're seeing is the overall effect, which is entangled. And this is about disentanglement. And a nice example, I think I mentioned it before, I'll go over it again, is when you're hearing a recorded speech, the product you're hearing is an entangled signal. It's entanglement of many causes in terms of what were the sequence of words uttered. That's the main content that could be transcribed, and you could type it in, right? You could have a speech recognition mechanism to transcribe it for you. But it also entangled with other things, such as the pitch, such as prosody. Prosody, pitch is a part of prosody. It's like the emotion of the speaker is an excited speaker. So that is part of it. And then the particular individual speaking, that has a term also called timbre. Timbre is a particular combination of frequencies that identifies the speaker. So we have timbre and prosody and content. So what you are actually getting is a combination of all of these. Then we can talk about, is it possible to take that speech signal off of the microphone and disentangle into separate signals? This is about the timbre, this is about the content, and this is about the prosody, and so on. Why would we want to do that is to understand the signal better, if there are any noise and things like that, you can get rid of it easier. You could also use it for converting speech from one person into speech of another, something like that, where it's the same person speaking in a different voice. You could do that, or maybe in machine translation and so on. So all kinds of uses for disentanglement. All right, let's take it that disentanglement is a useful thing. So once again, the title of today's talk is putting all these together in one phrase: semi-supervised disentanglement of causal factors. All right, try to keep all of them in mind together. How are we going to do all of this in today's lecture? Right, so what we're going to do today in today's lecture, you might have had a chance to look at the slides already. The slides are available on my public site, as well as those of you who are in the IASC class. I usually post it within Piazza for the class. So we begin with what is meant by semi-supervised learning. Oh, there is one more thing we could also talk about. Today there is a topic which has gained importance. Let me see how we can change the screen here. Okay. All right. Okay, good. So I was able to put the names of the speakers on top here. Okay. Okay, let's continue. So yeah, we're going to begin with self-supervised. There's a major topic today in machine learning, which is called self-supervised learning. Some people say that that is the most important new direction for deep learning, is self-supervised learning. So we are going to be talking about semi-supervised learning. So how is semi-supervised learning different from self-supervised learning? Um, right. So, semi-supervised learning I already mentioned. It's about data that is partially labeled. Self-supervised is slightly different. It's about having multiple signals, part of which has got supervision and part of which doesn't have supervision. You could have multiple modalities of data coming in, some of which is supervised and the other of which is not. So how to transfer information from one to the other? If you, for instance, if you're looking at a picture of a cat and you might have a label for the ear of the cat, can you use that and leverage that to say, well, if that is the ear of the cat, I have an idea of what the face of the cat is like. So you can label that part of the image as the cat's face, knowing that you have a label for the cat's ear, right? Maybe a quick example. Self-supervised learning also plays a role in attention models. There is self-attention models and so on. So that's a different topic. I hope I can give one lecture on self-supervised learning also after this is over. So anyway, today we're not talking about self-supervised learning, but semi-supervised learning. Those terms look quite similar. Okay, so we'll look at the example of a couple of examples of uh, semi-supervised learning and then of disentanglement. And we look at the speech example. I already mentioned what the components of speech are. And we'll also look at another example, which is another emerging area of deep learning called explanation-based learning. So one of the critics or complaints about today's deep learning is that an explanation of how what was accomplished is not readily available. If you have the causal factors disentangled, that becomes an obvious way of explaining why did you say it was a cat? You could say, well, they've disentangled the causal factors, that was the ears, the fur, and so on. So that's the reason I called it a cat. So that becomes an explanation of why you called it a cat. So we'll look at, these are all justifying what we're doing. And after that, we will look at what does it take for semi-supervised learning to be helpful. In not every situation you can find semi-supervision useful, and under what conditions of the distributions of the data can you find semi-supervised learning useful. Okay, so that's one of the topics. And there we will look at the variables that have causal influences. We looked at it last time also under transfer learning, about variables that are causes and variables that are effects. The same thing shows up here, saying when you have features that are that go towards the objective of the supervision signal, then supervision is helpful. We'll see a couple of examples of a distribution that is flat and a distribution that is multimodal, and find that the multimodal distribution might have a causality in it, which kind of is helpful for semi-supervised learning. So I'll have to go through the differences there. So anyway, let's leave it that we're going to look at under what conditions does semi-supervision become helpful in solving the learning problem, and then move on to finding salient features as a broad topic. Saliency, when you're looking at an image, what features of the image are salient, that are important for doing a task, and what features are not so salient? There might be all kinds of little detail in the background that might not be salient. We use the word salient. And so we conclude by discussing saliency and recognizing images with salience. Okay? All right, then let's begin with the slides for today, which is causal factors. I'm going to share these slides. Okay, good. So there is slide number 1. We are in section 15.3. Okay, hopefully you can see the slides now. It is titled Semi-supervised Disentangling of Causal Factors. Okay, so let's put it in perspective by the next slide, which says where does this topic occur? It occurs in the particular chapter on representation learning. And these are the 6 subtopics, rather interesting ones. We did greedy layer-wise unsupervised pre-training. That was about learning layer by layer in a deep learning network. That's a greedy system. And then we looked at transfer learning and domain adaptation, which was about learning on one data set and using what has been learned to perform on a different data set with a slightly different task. And what does it take to do the transfer learning is something we saw. And today is semi-supervised disentangling of causal factors. And the topic for next week will be on distributed representations. That again is a very fundamental topic about how all of deep learning is about distributed representations. It's not symbolic representations. A concept is not stored as this is the concept. It is distributed over several units. That's what deep learning is about. And then why, when we do this, we get exponential gains from depth in terms of number of possibilities and so on. And how to get clues for discovering underlying causes. So that's going to be related to today's topic, the last one. And the subtopics we look at today are these, which are causal representation, and then a relationship to semi-supervised learning, and then salient features. Among salient features, we'll talk about how salient features can be obtained from autoencoders, but they don't do as good a job as generative adversarial networks or GANs, which is an emerging topic. And we conclude with role of cause and effect in deep learning. Okay, this slide is about speech. So it puts it into a more concrete perspective, the nature of speech. So on the box on the top left, we have a description of 4 factors underlying speech. And the first of which is the language content C, capital C. It's a language content. So what is being said? So what is being said is transcribable to text. That is the main information content. Number 2 is timbre. Timbre is labeled here as a V, and it characterizes speaker identity. That's the combination of frequencies. Timbre also has got to do with like musical instruments. A violin has a certain timbre, a flute has a certain timbre. So you can recognize the same song on the flute or the violin, but you can still tell that they're apart, they're different, although they have the same sequence of frequencies. So timbre identifies the instrument, timbre identifies the speaker, characterizes the speaker identity. And then come 2 factors for speech referred to as prosody. And they capture speaker emotion. And the first of which is pitch variation, right? Frequencies going up and down and so on. Maybe somebody who's excited, maybe have higher pitch. And it's got aspects of the speaker tone, as they say. So pitch variation is F. And the last part is called rhythm, R, which is how fast the word syllable is uttered. Right? Is it very quick utterances or is it slow? So those are the factors underlying speech. And so the issue here is it would be useful for disentangling these factors. And the question is, why would you want to disentangle it? The disentangling can be useful in two different directions. One is speech analysis. You're just listening to the speech, and maybe we can remove irrelevant interference if you know all these four parts, and you can separate it out, and something that affects only the pitch or the timbre, maybe it doesn't have anything to do with the content. So it might be of value in removing noise. It can also be of value for speech generation, which is voice conversion. You can remove the pitch, and you can remove the timbre and maybe introduce new timbre to it. Or you want to modify the prosody emotion and make it flatter or something. So those are all things that one could do, but mainly we are understanding the signal better. Well, that's the entangled factors part. On the right-hand side is shown a simple autoencoder. This is an area of active research. So there isn't the best method. People are just beginning to understand this issue of disentangling speech signal. So this is an autoencoder diagram here. You can see the speech S is input at the bottom. Speech S or some version of it, S tilde, is produced at the top. There's an encoder here, there's a decoder here. We saw what an autoencoder was. We simply take the signal, we encode it into some representation, and from that we decode it into back to the original signal, and along the way we get some kind of a compressed representation. And in this particular case, the input speech has four parts: got the rhythm, the content, the pitch, and the timbre. So we say S is equal to ST is the sound spectrogram. The sound spectrogram has all these things as part of it, and it's all mixed, entangled. And that signal S is generated through an encoder G, which encodes the content, the rhythm, the pitch, and the all four parts, CVRF. That's what we have. So it takes all of that. That there's a generative model here that can take that and produce S. I guess this is for the decoder, right? S is generated, so the decoder produces that. Now, along the way, we also have U, which is the speaker identity, separately being input into the decoder. So it's a particular mechanism called an autoencoder for speech. And they were inputting the speaker ID back through the decoder. So the encoding part disregards the speaker part. There's a speaker part here, which is these cross lines here, the timbre. So it is extracting a signal without the speaker ID, and with the speaker ID put into it, it is able to reproduce the whole thing. So in a way, this is disentangling the three parts, not the speaker ID. It takes the speaker ID out and produces three parts together. It's not a full disentanglement, part disentanglement going on. And of course, there are other papers that have come out since this paper that actually tries to break it apart into all four signals, not three and one. So that is an example of speech and its entangled features and disentanglement. Okay, that's just one example. So let's talk now more about causal representation. So we can say in deep learning, we produce a representation H. I mean, it can be several levels. And then we keep on asking this question: what is an ideal representation H? So there isn't one absolute answer, but a good one is, One hypothesis of an ideal representation H is that it is a causal representation. So we are taking the signal and representing it in terms of the causes. We just saw what causes are, like we saw that for speech. So the representation that you get, either it corresponds to the underlying causes of X, right? Like we had the 4 causes, or it could be directions in feature space corresponding to causes. So it could be, after all, H is just a vector. And you can say that the data is concentrated in directions in feature space that correspond to the causes. It could be some combination of features that still represent causes. So that the representation disentangles causes. So it could be features or feature directions. And these causal factors can also be useful in explanation. And I threw in an example of explanation here, causal explanation. This slide comes from a talk on the role of explanation in deep learning. So there is today and tomorrow. Today's system takes a lot of training data. It learns from the training data. It learns a deep learning function. And when you input an image here, this is a picture that is input to this image, which has learned from all these examples. And the output says, well, this image on top here, this is a cat with probability equal to 0.93. So that's the nature of today's deep learning largely. Here is a user with a task, is scratching his head. All right, you took this image and you said this is a cat, and then the user is asking these questions. Why did you do that? Right? And why not something else? And then when do you succeed? When do you fail? When can I trust you? And how do I correct an error? So this is saying a deep learning system, when it gives you an answer, there are issues associated with the result it is providing. It could be those kinds of questions. And some of the research on explanation-based AI, explanation-based deep learning, tomorrow, this is not a solution existing today. Training data, the learning process is a new learning process. Same image is input. It is creating an explainable model. This explainable model looks like it's a causal structure. That's what we are talking about. Explainable model is a causal model. Causal model usually looks like a Bayesian network, nodes and pointing to nodes and so on. The parents are causes of the children, that kind of a thing. And so inferring through this model says this is a cat. Okay, same answer. Only thing is, it says by looking through the causal model, you can say it has fur, it has whiskers, and it has claws. And it has this feature, and it has this feature below. Look at the ears, the pointy ears here, pointy ears here. So the answer now is given as, this is a cat, it has fur, whiskers, and claws, and it has got these peculiar ears, characteristic of a cat. So this way, the user with a task seemed to be happier here, saying, I understand why you said it's a cat. I understand why not, because maybe human beings don't have these kinds of ears, I suppose. I know when you will succeed. It is saying something about the result. Perhaps it can be analyzed. I know when you will fail, because those are the kinds of features it depends on. I know when to trust you, and I know why you erred, what could be the mistake. So anyway, this is about the direction of research of causal modeling. Not all of those answers that we see on the right side are completely done, but it kind of indicates what kind of issues there are. And why I put this up here is when you have a model that disentangles the input into causal factors, that can be useful to provide an explanation, just another motivation for this line of research. So the broader question is, what what should be the nature of H that is produced out of X? We use H for hidden. X is the input, Y is the output. So the kind of H we get is a representation that is easy to model. It is something that has got a simple probability distribution, such as the features are all independent from each other. So we can say that the joint probability is the product of the probabilities. They're all independent. So probability of a cat is going to be equal to probability of fur and probability of ears and so on. If they're all independent, then you just need to multiply the probabilities. So a representation that is easy to model. It could also be a sparse representation that only some of the H's are ones and the rest are zeros, that kind of a thing. That's a sparse representation. Easy to work with as we move along layer to layer. So that is mathematically oriented representation that is easy to model, independence, sparsity. Or number two is representation that separates causal factors. That's the kind of thing our lecture is about. It is get the causal factors. The trouble here is it may not be easy to model. But anyway, for some tasks, the two coincide. So when you are able to get the causal factors, those are also a simple representation. Now this slide, there are two different probability distributions on this slide. I chose these two to put on one slide because one of them is useful for semi-supervised learning and the other one is not so useful. So the first one we're looking at is not so useful. So when is P of X is of no help in learning P of Y given X. So here is the distribution of X. It's what's called as a uniform distribution. It's flat between A and B and zero elsewhere. We refer to that as a uniform distribution. So X has that distribution. And so this is just a plot of P of X versus X. It's got nothing beyond a distribution over X. It has nothing to do about Y here, which is the kind of the answer we're going to be getting. And it's just telling it's flat. It's like telling you that the color of this image is black and white. It's not telling you anything more. Right? We are looking for something more about what we're trying to tell something and it's not telling you anything. It's simply saying it's flat. Consider another case where this distribution of X is has got three Gaussians here, three peaks. We refer to this as a multimodal Gaussian. And X has got three peaks. And those three peaks actually correspond to three possible values of the output, y equal to 1, y equal to 2, y equal to 3. So when we model P of X, it says that there seems to be a structure here with three peaks. So we can say maybe that corresponds to P of Y given X. So y equal to 1, y equal to 2, y equal to 3. So if this is the situation, and I give you, now we're talking about semi-supervised learning, I give you examples of X with a value Y. I don't have a lot of examples. A lot of examples of X were only used to give the multimodal distribution, but I give you one example each. Y equal to 1, y equal to 2, y equal to 3. So then you say, oh, okay, y equal to 1. That example corresponds to the first peak. Y equal to 2 corresponds to the second peak. Y equal to 3 corresponds to the third peak. That is extremely useful for me to be able to say, what is the distribution of Y given X? And I gave you just one example each or a small number of examples each. So semi-supervised learning becomes useful when the distribution that you have of the variable is of this nature. I just filled it in. What kind of data set could you give? Could you get this kind of a multimodal distribution? And what we have here is a children's book of learning to write uppercase and lowercase alphabets, capital A, small a, capital B, small b, capital C, small c, going up to capital Z, small z. And there are also the numerals 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 here. And we can think of the X that we are plotting as the amount of ink used in each of these letters of the alphabet and each of the numerals. So we can imagine the capital letters have more ink used in them. Capital A has more ink than small a. So we would say, well, X is the amount of ink used. The amount of ink used is more when the letters are capital, and there is a spread of it. It's not exactly the same, A, B, C. So maybe this last P corresponds to the ink used for doing capital letters. And then there are these handwritten numerals, which seems to be in between capital letters and small letters. Maybe the middle peak corresponds to the ink used in doing the handwritten digits. And then the peak with the least amount of ink used, maybe the peak corresponding to the small letters. All of them have some variation. That's why it's Gaussian. It's not exactly one value. But they're peaking around some kind of a mean here, the three means here. All right. So we can think of each of these y's as being univariate Gaussian, corresponding to y equal to 1, 2, 3. So we're saying the components are well separated by the feature x, and the modeling of PFX reveals where each component is. And a single labeled example per class is enough to learn Py given x. Supposing I simply say, take one example of each from here and tell you that is an uppercase, that is a lowercase, and that is a digit. So that's roughly enough to say that we now have a situation where we know the distribution of y given x. And so that given a new x, we can classify into y, because whether it falls into this peak or this peak or that peak, because you've told us with one example, right? So that's the idea. So I'm just seeing whether I can unmute your audios. All right, maybe I'll just leave it like that.
Why would you?
Still have difficulty with this muting and unmuting in case you had any questions to ask. Okay, let's continue. And so we are saying causal H is useful to predict Y. So if H represents causes of the observed X and outputs Y are among the most salient causes, then it's easy to predict Y from H. Right? So there are many causes for the image. And if the kind of causes we've identified are salient causes relevant to predicting a cat. If there are lots of things about the background, those causes are not as important as the salient causes. So if your goal is to classify as a cat, then they should be the salient causes. And the representation for P of X may also be good for P of Y given X if the output Y is among the salient causes of X. Example, cat Y influences the shape of the ear H. There can be many of these H sub I. H consists of several hidden causes, and maybe the cat influences the shape of the ear, which is what HI is. So what I've drawn here on the right hand side is it's a probabilistic graphical model rather than a neural network. It says Y is the output, X is the input. H is a set of hidden units in between. And I've written arrows going from Y to H and H to X. These kinds of arrows are in a probabilistic graphical model or a PGM. It says Y is the cause of H, and H is the cause of X. So the image that you see is caused by these hidden features H, and the hidden features H are caused by Y. So in a way, this is a causal Bayesian network. And what is the inference we're going to be doing with this kind of a probabilistic model is that the inference is, we say, is anti-causal. That we are given X, from X we got to infer H, from H we got to infer Y. Right? So in a sense, we're going in the opposite direction. The causality is top to bottom. Inference is going in the opposite direction. And from X, we want to tell what is Y. Right? So we're saying if these H's or the Y's are such that they are the salient causes of X, then the task is simplified. Okay, this slide says semi-supervised learning is useful in anti-causal problem. So we talk about the same Bayesian network being used for slightly different tasks. So we have, this is actually a Markov network, X and Y, right? So this corresponds to the ID, and this corresponds to a function from X to Y. And we kind of written more in terms of a Bayesian network over here. So in this example, we are taking as input an mRNA sequence that is X. And that mRNA sequence is able to predict the protein Y. So this goes X to Y. So mRNA sequence is the X and Y is the protein. In a way, this is a little bit like, I guess if you don't know much about mRNA sequence and a protein, how about rain and umbrella, right? X is rain and Y is umbrella. So if it rains, the umbrella is open. If it doesn't rain, umbrella is closed. So it's a causal problem, left to right. So we are predicting protein Y. It's not an absolute deterministic thing. If it rains, there's a good probability that the umbrella is open. So we are able to predict it with some probability. This other one is predict class X from handwritten digit Y. The model looks similar to this, X to Y. X is the digit class, 0 through 9. And Y is the handwritten digit, a particular image. And so, but the problem here of inference we have is not going along the direction X to Y. We're going from Y to X, in that I've given you a handwritten digit and I need you to predict the digit class for me. So we say this is a anti-causal problem rather than a causal problem, predicting the. So one was a generative model, the other one was an inference problem. Okay, so what does this tell you is that modeling PFX with extra data does not help in example 1. So we had more data to model this distribution of X exactly. Or let's take a look at the rain and umbrella case. So we have a better model for rain, but it does not help us predict the causal side of things, right? So it doesn't show the relationship between X to Y. So it's just X is being modeled. We assume that P of X is independent of P of Y given X. So that's another thing. When you have a Bayesian network like this, if you remember a little bit of Bayesian network, the joint probability distribution of this figure here is P of X times P of Y given X. What it says is P of X is independent of P of Y given X, right? Which is why any change to X does not have an effect on Y given X. Right? Mathematically, we can justify that. But in example 2, modeling P of Y is helpful. So here, P of X given Y is dependent on P of Y. right? P of x given y is dependent on P of I by Bayes rule here. So if I have extra data for the handwritten digit, okay, that is helpful. It says if I had more examples of handwritten digits available, then that is helpful to solve this problem of inferring x to y. Again, intuition-wise, it says if I tell you about the distribution of the handwritten digits more, then I learned something in classification. But if I tell you about how often you encounter the classes in this direct model, that doesn't change anything. Of course, that could be used as a prior probability, but that's not what we're talking about here. And that is what is being said here. Okay, so for the anti-causal problem, supervised learning is useful more so than in the causal problem. So semi-supervised learning is possible when factors are disentangled. So what could tie P of y given x and P of x together is if y is closely associated with one of the causal factors, then P of x and P of y given x will be strongly tied. Right? So we're saying if the class is closely associated with one of these factors. And unsupervised learning that disentangles underlying factors is useful for semi-supervised learning. Okay, a little bit more of the probability analysis here. So the best possible model, we're trying to formalize it. So assume that y is one of the causal factors of x. We're talking about y or one of the h. Y is the final output, h is something in between. So let h represent all those factors. The true generative process is conceived as structured according to this directed model with h as the parent of x. So in the sense we have h as a parent. So in which case the joint probability P of h comma x is written as P of h times P of x given h. I just mentioned this in the previous diagram. That is the nature of the joint probability distribution. And we can say thus the data P of x has the marginal probability. This formula expectation with respect to h of P of x given h directly arises from this point that if you wanted probability of x out of P of h given x, h comma x, you would have to marginalize the h variable by summing over all possible values of h. And when you do that sum over all possible values of h, I can write this as an expectation with respect to h of P of x given h. So the data has the marginal probability x given h. Thus we conclude that the best possible model of x is one that uncovers the above true structure with h as a latent variable that explains the observed variations of x. So this is saying that the distribution of x is modeled by this conditional distribution x given h, and that captures the distribution, and that is what is being exploited. So ideal representation for learning is it should recover the latent factors. It's a very common sense thing also. We're saying to recognize cats, you get features corresponding to ears and so on, and don't get me features that are irrelevant. So this thing should recover the latent factors. If y is one of these, then it'll be easy to predict y from such a representation, and also justifiable from Bayes rule. And the marginal P of x is intimately tied to the conditional P of y given x. So the knowledge of the structure of P of x should help learn P of y given x. Therefore, in situations respecting these assumptions, semi-supervised learning should improve performance. All of this is trying to explain the same idea. When you had that three-peaked distribution, that is helped with supervised learning. So most observations are formed by an extremely large number of causes. And by simply learning all the causes is not a good solution. And brute force solution, unsupervised learning, a representation that captures all the reasonably salient generative factors, disentangle them from each other, thus making it easy to predict Y from H, regardless of which HI is associated with which Y. And the brute force is infeasible because it's not possible to capture all factors of variation that influence the observation. Example, in a visual scene, should the representation encode all the small objects in the background? So this is like the scene with the cat has lots of pebbles and lots of plants and all that in the background. All of that is causing the visual scene. And should the representation encode all the smallest objects in the background? And if you look at humans, we fail to perceive changes in the environment not relevant to the task they're performing. So the research frontier in semi-supervised learning is what to encode in each situation. Okay, here is an example of an object with saliency and without saliency. Look at this first picture here. And we ask the question of people, what have you seen? We just show you this image and ask you, what have you seen? And the answer could be, well, I've seen a lighthouse. Or another answer could be, I have seen a lighthouse and houses. Third answer could be, I have seen lighthouse and houses and some rocks, right? So it has got all of these answers. So all of these are the causes of the image. And so the question comes in as, what are the salient ones? So there are two ways to deal with many causes. Two main strategies to deal with a large number of underlying causes is to use both supervised and unsupervised learning, which is to use a supervised signal at the same time as the unsupervised learning signal, so that the model will choose to capture the most relevant factors of variation. Right? So we're saying if you use not only the unsupervised learning, which is getting all the causes, you're also saying it's got a lighthouse or not. So the supervised signal is useful. Use a much larger representations if using purely unsupervised learning. There is no supervision signal. Then of course we'd need a much larger representation. So then this has been a topic of some study in computer vision about saliency. So an emerging strategy for unsupervised learning is to modify the definition of which underlying causes are most salient. Autoencoders and generative models usually optimize a fixed criterion, say mean squared error. We saw autoencoders. We are going to be arguing that the autoencoder based on mean squared error is not so good because it encodes everything. These fixed criteria determine which causes are considered salient. And if mean squared error is applied to pixels, implying that an underlying cause is salient only if it significantly changes the brightness of a large number of pixels, it's problematic if the task involves interacting with small objects. So if you use simple mean squared error about the brightness and so on, this was a project they did where the autoencoder is trained with mean squared error. You remember in an autoencoder, we go from input to output, but we use some kind of a loss function to backprop to learn the weights. We were using mean squared error here, or the maximum likelihood criterion. And the autoencoder trained with mean squared error for a robotics task fails to reconstruct a ping pong ball. So there was an image here input, a small little thing, ping pong ball. It didn't reconstruct it because it seemed to be a noise or something like that. So the existence of the ping pong ball and its spatial coordinates are important underlying causal factors that generate the image and are relevant to the robotics task. This was for a robotics application where that ping pong ball had to be picked up by the arm, and that is not being encoded. So the autoencoder has limited capacity, and training with mean squared error did not identify ball as salient enough. So same robot succeeds with larger objects. such as baseballs, which are more salient according to mean squared error. So it says if you simply use an autoencoder, it might miss things that are salient objects just because they're small. And so other definitions of salience. So we can't simply leave it to a simple mean squared error to determine saliency. You need a better definition of salience. So if a group of pixels follows a highly recognizable pattern, even if that pattern does not involve extreme brightness or darkness, then that pattern could be considered salient. So it's saying it's not just the dark brightness of that pattern, but it is some relationship between pixels. So one way to implement such definition of salience is generative adversarial networks. So if we encounter again this idea of GANs, so GANs are famous as generative models to be able to generate images. So a GAN is a generative model, or it has a G network and a discriminative network, D network. The generative model is trained to fool a feed-forward classifier. This figure kind of explains what do you mean by fool. This is a training set here of handwritten digits. And this is a generative model which generates images and which are realistic. And this discriminator D attempts to recognize whether the samples came from the generative model or they came from the real training set. So the generative model itself, of course, has to be trained from the training set, just like an autoencoder would be a generative model. And the discriminator has to tell whether it's real or fake, where it's coming from. So the generative model tries to do as well as possible in generating realistic images, and the discriminator model is trying as well as possible to discriminate between the two, which means the entire model, the generative model is learning what are the important things that distinguish between the two. Like we had missed the ping pong ball, something like this would pay attention to small things that are significant. And such GANs can determine saliency. Any structured pattern that the feed-forward network can recognize is highly salient. Right? So the D network is trying to say, well, you didn't get that part. Right? It's like a teacher telling a student, do this task, and the student misses it, and it's saying, okay, you missed that. So student relearns it. So GANs learn how to determine what is salient. So here we are comparing the mean squared error versus GANs. Models trained to generate human heads and neglect to generate the ears when trained with mean squared errors, but generate ears when trained with GANs, because the ears are not especially bright or dark compared to surrounding skin, but their highly recognizable shape and consistent position means the feed-forward network can easily learn to detect them. So this was some experiments here. Predictive generative networks. These are the original images. The ground truth is correct image that the network should emit. The mean squared error, like the autoencoder, a network trained with mean squared error alone, considers ears not to be salient to learn to generate them. So it is generating things which have a much better contrast quite nicely. It is forgetting about the ears here, where an adversarial model trained with mean squared error and adversarial loss. So we have to define what is called as an adversarial loss function. There are all kinds of ways of defining it. Right? When we study GANs, I'll mention some of those. Right? So many varieties, hundreds of GANs that are around. And for example, the famous one is called Wasserstein GAN. It uses a Wasserstein loss function. And by using an adversarial loss function, the ears are discovered to be salient because they follow a predictable pattern. So this is a subtopic in computer vision, research on determining salient features. GANs are only one step toward determining which factor should be represented. And ongoing research is on ways of determining which factors to represent and develop mechanisms for representing different factors depending on the task. So there are many papers. This is one interesting paper with some figures I found. Saliency detection using something called supervised adversarial networks, which discovers the salient parts. And these are images from top to bottom, 1, 2, 3, 4, 5, 6 images. And these are the ground truths available and different models that are saying which parts are the salient parts and which are not. They're being highlighted here. These are different models along the way, baseline 1, baseline 2, and then the salience model that their paper describes, saying it tells you that these are the salient parts. And it's got all of this detail here and it's breaking it down, saying that those are the salient pieces here. I suppose look at this one, maybe it's the clearest one with a girl on a bicycle here. It's giving you only the girl on the bicycle and ignoring all the hedge and all kinds of things in the background, saying that's the most salient part here. So this is saliency detection. Anyway, my final slide is that invariance of causal factors. Causal factors tend to remain invariant. Hence, generative model that attempts to recover the causal factors should try to look at causal factors that do not vary over images or transformations and so on. Okay, so I shall stop there. You can ask any questions. I'll see if I can unmute. I'm having some difficulty with this part. Okay, so if there are no other questions, we can discuss any issues you have offline. Okay, so I shall stop here. Monday's lecture will be on distributed representation.